Hello everyone, today we're working with a calculus problem. We've got a related rate problem. And let's go ahead and look at that. So you've got, if the top of a 15-foot ladder is sliding down a wall at 1 foot per second, how fast is the base of the ladder moving away from the wall when the top of the ladder is 3 feet from the ground? Okay, so when we're working with related rates problems, there's several things that I'd like to do. I do these more just to organize what, our material and our information, because there's a lot going on with these problems typically. So first of all, I'm going to draw the scenario that's going on. So we have this ladder right here, and we have a wall, and this ladder is 15 feet long, and right, the idea is that it's sliding down, and at each second that goes by, it looks like it's sliding down the wall, and the bottom is moving away from it. Okay, so that's the scenario we're looking at. So I like to draw the picture first of all, because it kind of gives you an idea of what we're looking at. And sometimes this might take you a couple minutes, which is fine. You take your time with these problems, so you have a right idea of what's going on here. All right, and the next thing I like to do is, what I would call step two. Step two basically is I'm going to label in this picture things that are moving, quantities, or parts of the picture that are moving. So the bottom of the ladder is sliding down. So that, let me call that distance y from the top of the ladder to the ground. That's changing here. And the distance the bottom of the ladder is away from that wall, call that x. That's changing as well. So I'm going to label that with an x. Okay. The ladder itself, where it's 15 feet long, a lot of people will say, oh, I'm going to label that as a variable too, because it's in the picture. I would highly advise against labeling anything that you know is a constant already. Just leave it as a constant. Okay, so we labeled things that are changing with a variable. For step three is I'm going to ask you to find the rate that we're looking for and the rate we're given. So the question here is, how fast is the base of the ladder moving away from the wall, and etc. Now, I really just need that part to say what I need to find. And that would be, how much is the bottom of the ladder moving away from the wall? This is how I would describe that, dx dt, okay? So what I'm saying here is the rate of change of x, the distance the bottom is away from the wall with respect to time. This is what I'm looking for. And technically speaking, it's when the top of the ladder, this is where the rest of the information would be handy. The top of the ladder is 3 feet from the ground, so this is where y would equal 3. One thing to note, this is very important. When you write dx dt or dy dt or whatever rate you're given here, when you're writing rates, that's how we describe them, with that notation, or sometimes we say x prime. Typically with related rate problems, it's dx dt, dy dt, etc. You're making an assumption here, and that assumption is that when you say x dx dt, you're saying that x itself is dependent on t. So x is a function of t, okay? And that's going to be important when we start taking derivatives in a second. We'll go more into that. All right, we also have a rate that's given. We know dy dt, okay? We know that the top of the ladder is sliding down the wall at a foot per second. So for every second that goes by, the distance goes down by a foot, so minus 1 foot per second. As you can see, I wrote the units of the rate, feet per second. You don't need to do that. However, you do need to know at the end of the day, what the rate that you're using is, the units are. Feet per second, miles per hour, you need to know that. And another thing, just real quickly about these problems, is sometimes you're given different rates in terms of measurements. One rate is feet per second, the other one's mile per hour. You really need to work, in my opinion, to make this as easy and as coherent for you, is to use one single rate. So I tell people, if you have different rates, convert them to one single unit. It's up to you what you want to choose. Okay, so we've gone through our steps up to 3, and here's step number 4, not 2, which I think is the most difficult one actually is to come up with an equation. The equation that you have depends on the scenario that you're looking at. A lot of the time, if you're looking at a geometric problem that has a geometric interpretation like it does here, you can use a fact from geometry. So for example, here, if it makes sense, I have a right triangle and I can use the Pythagorean theorem. X squared plus y squared is equal to 15 squared, or 225, whichever. Okay, and that's the equation that relates all my variables. And yeah, that might take you a second or two or a couple of minutes or 10. It just takes time depending on what's given. Okay, now step 5. I'm going to take a derivative, because at the end of the day, I'm looking for a rate of change, a derivative. I need to take a derivative of something. I'm going to take a derivative of this equation. So I'm going to take a derivative with respect to time. So you can have d over dt of x squared plus y squared equals d over dt of 15 squared. And you are going to use a couple more properties here. D over dt of x squared plus d over dt of y squared equals d over dt of 15 squared. And what's d over t of x squared? It's going to be 2x dx dt. So going back to what I wrote earlier about x and y being functions of time, when you take the derivatives of x with respect to time and y, you're doing an implicit derivative. So the derivative of x squared is not just 2x, it's 2x dx dt, because x itself is a function of time. You're doing a chain rule here, okay? And that always happens with these related rate problems. Very similarly, you have 2y dy dt, and what's the derivative of 15 squared? It's just 0, okay? Yeah, 15 squared is the way of writing that is 225 if you prefer. I don't care about that. It's really just a constant. Number 6, we got our derivative. I'm going to now solve for what I'm looking for. I'm looking for dx dt, and dx dt, I'm going to solve for that expression. It's going to be minus 2y dy dt over 2x, just 2x. And yeah, a couple things here, the 2's cancel, and you would have dx dt equals minus y over x times dy dt. Now, I want a rate at the end of the day. I don't want just what you see here. I want to, in other words, I want like a number. So I'm going to replace my y and my x with what's given in dy dt. I actually know that dy dt is equal to minus 1. I'm not going to include the rates, but you can. We were interested when the top of the ladder was 3 feet from the bottom. So this is going to be negative 3. And what's x? Well, we don't know that. Okay. All the picture at the moment where the top of the ladder is 3 feet from the bottom, all you know this is 3, and all you know this is 15 right here. And I don't know what x is, but you can find that by using the Pythagorean theorem. And oftentimes, yeah, it's the equation that relates all the variables that you can use again. So 9 plus, we'll call this x squared equals 225. X squared equals 225 minus 9, which is 216. So x equals the square root of 216. And I'm just going to plug that in. So it's going to be 3 over the square root of 216. And this is in what units? It's in feet per second. Okay. Because my rate was, a couple things to note is like, yeah, the rate itself is in feet per second that was given to us, dy dt. That's one thing. And the other thing is, yeah, I don't have any other values other than feet and seconds here. And the other way to look is that you're given 15 feet here. We're talking about feet. And the time here is, yeah, in terms of seconds, as given again by the rate. Okay, so you get that 3 over root through 216 feet per second. Now, can you simplify that square root of 216? Yeah, you can. I really don't care about rationalizing denominators or factoring numbers out of that radical. It's not the point here today. You can leave the number as is, or if you prefer, we can figure out what this number is approximately. Yeah, because no one really goes by saying, oh, the rate of change is 3 divided by 2, square root of 216 feet per second in real life. We want a decimal approximation maybe. In our case, we have 0.204. I'm going to leave it to 3 decimal places. So 0.20 feet per second would be your answer, okay? All right, so again, several steps that you follow. I would just go back and look at all the steps that I wrote. I don't want to go back and review because it was a lot. But thank you so much for your time and your patience throughout all this, and I hope this helps.